pleasure to be here. And I guess we all know by now that the goal of computer vision is to give the computer the ability to see as humans. But today I'm going to talk about a task in which computer vision can do better than us. Just before I start, it seems like my talk is among the very few talks that doesn't involve any deep learning. So beware, and I hope you'll survive. So when we observe objects that are captured in digital images, we often associate them with ideal models. For example, perfect geometries like circles, or perfectly straight lines, like in these examples. In other cases, when objects repeat themselves, they may look almost identical to our naked eye. It's very hard for us to notice any subtle differences between them at the first glance. But we all know that in reality, there is no flawless behavior, and objects always deviate from their ideal models. So in this example, some of the dancers are taller. There is irregular spacing between few of them, and this dancer tends to bend her knee a little bit more. So in the next few minutes that I have, I'm going to tell you how can we completely automatically, just from a single image, can reveal and modify deviation from ideal. So now the question is, how do we define what is ideal? And I'll consider two models. One is perfect geometries, like circles, lines, ellipses, where the model is known and parametric. And the other definition is perfect repetitions, like in the dancer's example. And here, the model is non-parametric, unknown, and should be estimated from the data. So I won't have time to go into the technical details, but I would like to show you where this could be useful. And I'll start by showing how can we reveal deviations from ideal geometries. So let's assume that I want to buy this house. And we all know that the roof should be a straight line. And any subtle deviation from straight might indicate structural problems with the house. So what we can do is completely automatically detect very subtle sub-pixel deviation from a perfect form and magnify them. And if we do that and magnify them by 8 times, we can reveal that the roof has started to sag, just by having this image as input. In this example, we took an image of the Big Bang, and we feed to this image vanishing lines. Vanishing lines are lines that are parallel in 3D. We consider 2 of them to be the perfect model that the tower should comply with. And we compute, again, the very invisible small sub-pixel deviations from this perfect model and magnify them by 20 times. This is the result. So we can actually reveal that the tower is tilting, and it's actually in the same direction as measured by civil engineering. So here you can see it again. Let's turn to deviations from perfect repetitions. And if I'll go back to the dancer's example, here we can automatically detect all the various variations between the dancers, pose, height, and spacing. And we can reduce them and produce an idealized image in which all the dancers are much more similar to one another. So this can be seen as a graphical tool to beautify and idealize images by computing the deviations from perfect repetitions. And if we flip between the input and the corrected images, now that you can see that all the variations between the dancers suddenly pop out. So we can also go to the other direction and exaggerate variations. If we do that, we get a caricature of this image in which all the differences between the dancers are highlighted. We can take this piece of corn and warp its kernels to be more uniform and aligned in rows. And again, by exaggeration, we can highlight all the differences. So it turns out that repetitive structures also exist in complex textures, like the zebra stripes. And by exaggerating the differences here, we can reveal invisible curvatures that are present in the zebra stripes. And it's pretty hard to see it from this image, so let's have a look on these zoomed-in regions. So this image is an image of a painting that tries to give an illusion of 3D. By exaggeration, we can reveal very small, subtle brush strokes. We can do the same thing for color, basically exaggerating color deviations from a perfect model, which is an image with a uniform color. And in this example, it is possible because the lizard has a very similar texture as the background. And if we amplify the color variations in this case, we can basically segment out the lizard from the background. This is a controlled experiment that I did. I went to the supermarket and I got 6 tomatoes, and 5 days later, I went again to the same place and got 3 more. Can you tell which tomatoes are fresher than the other? Probably difficult. So if we exaggerate color differences, it becomes much more obvious. So purple shades indicate riper tomatoes. So our method is not supplied with any semantic information. So sometimes weird things can happen. So like in this example, we don't have any notion of a person or a face. So we can correct this image, but of course it will distort the faces as well. So I showed you how can we automatically reveal and modify deviation from ideal models and its application. We have more applications that I couldn't include in this small short keynote. So please see the website. I showed you how can we beautify and idealize images using this tool. How can we reveal surprising information about our world or create humoristic and artistic images. Thank you.